Very good afternoon, one and all. We are learning the subject of your the circuit theory or the network analysis, and we are studying the chapter of your the two-port network. So, in the two-port network, last topic is nothing but your the network functions. Okay. So what is the two-port network? Already one of the method that is nothing but the two-port network, Z parameters, Y parameters, all the methods we have seen how we can simplify the network, how we can reduce the network, how the complexity in the network can be reduced by using the different methods that we have studied with the help of all the parameters. This is one of the what we can say the method by which we can reduce the complexity in the network. Okay, and that is possible with the help of the transfer function by using the poles and the zeros, as well as the by checking the stability in the network, so that we can control over the network by looking the input as well as the output parameters. So here one by one we will see what is mean by the transfer function, how the Laplace functions can be affected on that, how we can identify which are the poles on which graph or the section we can call as a poles or the zeros, how they can denote it, and how we can find this circuitry is the stable or not, whether my circuitry, whether my network is stable or not. That all these things we will check here in this session. So in the transformation function, that is, or the transfer function of the network, that we will see in this case. So what is mean by the transfer function? If we are having the network, if the input port and the output ports are connected, the number of terminals are also connected to that networks. Okay, already we have gone through what is mean by the one port, what is mean by the two port and the multiple ports, how the terminals can be connected to that ports, how we can simplify the circuitry. Similar to that only, here is the plan of the network. In that the two signals are there, that is nothing but the input, as well as we are observing the output, the changes which is going to be happen by using these methods, that you can observe with the help of this transfer function. So in short, you can say the transfer function is nothing but the ratio of your the Laplace transform of the output to the Laplace transform of your the input. So in short, with the help of the Laplace transformation, we are going to implement using the what you can say the network function. Okay, with the help of the Laplace transformation only, it is possible to simplify the network. That is nothing but that is also known as your the transfer functions. Okay, so here at the input side there is a u of t, and the output side a y of t. In many of the textbook they are referring that notation as a different way, they are using any different, we can use any different, but here at present if I am using the u of t, that is considered as the input, whereas the y of t is nothing but the output, and the ratio of this output to the input of your the Laplace is nothing but, that's why we are written here the notation of L, that is nothing but Laplace of the input. Okay, the Laplace of input, that is with respect to the time period of t, that we can convert. Okay, in the frequency domain, that is a u of s. Similarly, Laplace of y of t, that is the output terminal or the output ports, that will be converted afterwards, that is after Laplace transformation, that is in the what we can say for time domain to the frequency domain. Okay, so here y of s will be there. So the in short, you can say the L will be treated as a Laplace operator. So in this transfer function, the transfer function is denoted by g of s. By the definition of your the transfer function, this g of s will be equals to output divided by input of your the Laplace transformation. So here output is nothing but the y of s, which is converted after the by taking considering that inputs, and we are converting into the Laplace transformation, that is a time domain to the frequency domain. Similarly, output divided by the input. Okay, so here this converted transfer function by using g of s of the plant or the network. So how we can get after getting that Laplace transformation? Initially it was u of t and the y of t. Okay, at present at initial stage, but whenever you will do for go for the Laplace transformation, definitely that what is time domain will be converted into the frequency domain. Okay, so and we can find that ratio is nothing but here the transfer function, which is denoted by g of s. Similarly, why we are preferring this Laplace transformation, that is too important here. So by using the Laplace transformation, we can convert many common functions into the algebraic function. or you can see the complex variables. So for the reduction, for the reduce the complexity, for what we can say, to get the simplest form that network, so we always prefer the methods. Okay, so this is Laplace transformation is one of the method by which you can simplify easily. So here if you observe this Laplace of your sine of omega t, this is the example. So L of sine of omega t, if this is the case and the output is omega divided by square planes omega square, definitely this will be converted into e raised to the power. Why I am taking e raised to the power is because there is no as such the initial is there, except with this a. Okay, this omega will be converted into the a after the Laplace to the time domain to the frequency domain. So L of e raised to the power, because s is equals to, later on it will be changed, that angular frequency will be changed, this s we are not having the additional part. That's why this Laplace of e raised to the power minus of at is equals to 1 by s plus a, where the s is nothing but the complex variable in the frequency domain. Okay, so that is possible here. Similarly, in the Laplace transformation derivation, so how we can identify Laplace of d of x of t divided by dt. So how we can convert this s of x of s minus of, means we are applying the orders. If you are taking the d by dt something, that definitely it will be the zero. If depending upon this x s order, if it is in the multiple, that is nothing but d square x of t of dt square likewise. So definitely it will be the twice and the thrice, that is a s square of x of s, then s of so and so, and then last part will be your the dx of dt. So likewise you can convert the things, that is nothing but in the Laplace transformation from the time to frequency domain. Okay, so here the simple expression and the calculation is mentioned how we can convert into the algebraic expression. So similarly, in the Laplace transformation derivation, if you observe, if you are having n orders, so that is nothing but Laplace of d of n of x of t divided by dt of n. This n will be the number of orders. Okay, so s raised to the power, how many powers? Order 3, order 4 likewise, and x of s will be here. Okay, after conversion, so summation of all means the total minus of the constant terms. If we are having a total, maximum is a 5, so then a decreasing form, which is the next, then which is the next, then which is the next, likewise we can simplify this one. Similarly, if you want to convert into the frequency domain, so how it is possible? That is the Laplace of integral of x of t of dt is equals to 1 by s x of s. So see here, this is in the form of your the time domain. Okay, and this is in the form of your the frequency domain. How we can do the calculation work related to the transfer function? Okay, so we should identify easily by looking the terminals, by looking the values, we can by looking the notations, what is our inputs, what are the outputs, how we can simplify, which are the orders, that is too important. Okay, so we know very well by looking the previous slides, we can identify easily y of t is nothing but the output, whereas x of t is nothing but your the later on after conversion, if you're taking, if you're considering this, if I am considering my y of t is the input, the notation may be anything. Instead of taking the u of t as the input, you may take the y of t, then later on you can change that y of t, that is in terms of your the x of t. So both are not x of t with the final one. Okay, so that x of t is nothing but the output, whereas the y of t will be nothing but your the input. So this ratio is nothing but the Laplace transformation. So if depending upon again the order 2 is there, then how we can identify the second and the third? So likewise d square x of t of dt square. So these terms, these are nothing but the, what we can say, the derivative of the input terms as well as the derivative of the output terms. So output minus of the input, this is the output, this is the input. So input you can take, so input minus of output in the form of your the derivative. In this way you can simplify in terms of the frequency domain. Okay, same thing is here, how we can representing the initial condition, how we are going to apply, how the order is going to be changed, how that what we can say, the output term in terms of the time domain can be converting in the, what we can say, you are the initial stages of, okay, initial stages, that is shown here, how the we can, how we are going to rearranging that equation, that is shown here. Similarly, this such type of expression might be you have studied in the maths also. Okay, how that outers are coming, how the transfer function can be converted of that is in the form of your the g of s, that is a Laplace of your the output divided by Laplace of your the input. So all these things we are applying by considering that zero initial condition. It means at the beginning they are starting from the zero. Okay, they are static from the zero. So it's a totally depend upon key which terms you are taking. So if output I am here the every time that the changes, if I am considering my y is the output, definitely y of s will be in the frequency domain. If x is the input, so definitely x of s will be the in the frequency domain like this. So y of s divided by x of s, here how they are going to be right in terms of the in the proper way. Okay, how the denominator and numerator, how the polynomial numerator, which numerator and denominator of your the polynomial can be affect on the transfer function, that is here what is you can say the mentioned here. And which whether that the orders, that is nothing but the n and the m comparison. Okay, m and as well as the n is the orders, n is the apostrophe, so that you can compare whether it's a proper or improper. So finally you can, in short, you can say that the transfer function can be used to check the stability of the system. You can say how we can say the stability of the system if that everything is in the controlling form. After applying the initial conditions, after getting the final conditions, if the system is working in the smooth way. Okay, the output as well as the input terms by transferring from the what we can say the time domain to the frequency domain, so that time you can say the system is stable. Again, secondly is nothing but the transfer function is applicable for the time domain and the frequency domain characteristics of the system. No doubt at all, it's a various easiest form to convert anything from the frequency domain to the time domain and the time domain to the frequency domain. That's why we are going to prefer the system in the transformation of your the time and the frequency domain. Third thing is nothing but the response of the system for any given input. Whatever we are applying at the input is there is no as such limits and the criteria. So that's why the response of the system for any inputs, whatever we are passing, that you will get the response of that. Okay. Now come towards the next, that is nothing but the poles and the zeros along with you the stability. Okay, poles and zero along with the stability. So here we will start with the stability. There are the several meaning of the stability, no doubt at all. The stable system. Okay, so generally there are two kinds of stability. While you are learning about the network as well as the control system, that is nothing but the absolute stability as well as the relative stability. So what is mean by the stability of the control system? See here, what is mean by the poles and the zeros. If you observe the ratio in the time domain as well as the frequency domain, that is nothing but y of s and the x of s, and you are writing that expression in the polynomial. So at that time, the roots of the denominator of the polynomial of the transfer functions are called to be the pole. Okay, denominator terms. So here the z is nothing but the zero, whereas the p is nothing but the poles, and the z by p is nothing but the poles, that is in the denominator. Okay, so p will be at the bottom, z will be on the top. The z by p, z will be the numerator and p will be the denominator. So in the poles of the systems are represented by X. We remember these are the notation by which you can understand easily how we are going to simplify the numerical with the help of using this stability of the system with the help of the input and the output poles and all. Poles and zero. So here the notation will comes here in the system. Whenever you are finding any kind of system and you are observing for the poles and the zeros, so definitely we remember the x is nothing but the poles of the system are presented by the x and the zeros of the system are presented by 0. Okay, so in many of the textbook, instead of writing the zero term, they are preferring that is a p as well as the z. Okay, many of the textbook they are preferring p as well as the z. Z will be indicating the zeros and p will be indicating the pole. So in this case also the system order is always equals to the number of poles of the transfer function. Now see here how the what we can say the output and the input ratio in the form of your n number of things are there, and how we can write in terms of the what we can say the polynomial that is mentioned here. So again, in this case, if poles is defined and it is a frequency at which it becomes the infinite, hence the name pole where field is infinite, because we don't, in the poles we are having infinite number of things. Okay, pole that is in the denominator also. Okay, zeros are in the numerator. The zeros is a frequency at which it will becomes, okay, zero. So frequency which is going towards the zero and the frequency which is going towards the till the infinite, so that terms will come. Okay, so zeros and the poles. The pole is the, okay, getting. So I will show you in terms of the graph also. In the further slide, there are the graphs, so we can identify easily at which particular point we can identify this is showing the poles, and on which particular point it is showing the what we can say the zeros form. So poles here in the frequency domain especially. Okay, so y by s. This is again then see here the infinite. Why we are looking for that stability of the system is also mentioned here. Why we are preferring this poles and the zeros. If you observe this figure, if you're talking about in the space and all, and for the wireless or the wide transmissions and all, see here the frequency ranges is very difficult to identify, uh, because we are considering it's an infinite. Even though we are having the few range of the frequency depending upon the application, still it's very difficult to simplify the thing. So that's why how the visibility of the light, how the light will propagate, how the frequency ranges are changing every time. So this tracking the getting the stability of the system is very difficult. So with the help of this method, we can simplify, we can try, we can eliminate most of the things, so that the signal will, whatever the signal which is passing from the input towards the output side, we will get in the proper way. Otherwise, it's very difficult to get the exact signals which is coming from the input side. Okay, so here the frequency responses. If you simplify, if you want to observe in the 3D form, at that time also it is very easy to identify in the vertical, in the horizontal, as well as in the slanting. That's how we are telling about the, we are talking about this 3D. The word 3D is nothing but that showing the information about the top views, the what you can say, top views, you can say the bottom and the side view. So we may call it's a vertical, horizontal, and the slanting. So in short, it's a relationship between the poles and the zero that we can identify easily with the help of the frequency response of the system by using this 3D, and that showing the poles and the zeros. So see here the notations. Okay, so here how we can simplify the transfer function calculation, that is the g of s is nothing but the transfer function. Here is the output divided by input of that, and if you are considering the vectors or the simple terminals, that is nothing but depending upon the orders. So a, b, and the c. Here is the first order. Okay, here is the middle part, and the last is the constant terms. That's why the denominator polynomial, that is nothing but the as plus b, will be equals to treated as a zero. Okay, if this part is treated as a zero, definitely the small s will be equals to, after equals to, this is a plus, as plus of b is equals to zero. As plus b is equals to 0. So here if I am taking this s, so s will be equals to, b will go there, so minus b divided by the a. That's why we can simplify, we can substitute the value of s minus b by a whenever you are getting that values. Okay, so now here again, how we can determine whether the transfer function is the proper or the improper, how we can identify the poles of the system, how we can identify the zeros of the system, how the order of the system can be implemented. So by looking these equation, we can easily identify what exactly we are doing. By looking these expressions, we are trying to simplify the numericals and the calculation work, or you can say the mathematical expression we are trying to simplify. How we can simplify with the help of the transfer function, that is nothing but we can, by looking these, we must to identify that is whether my transfer function is a proper or not improper. Secondly, how number of poles, how many number of poles are there, how many number of zeros are there, what is the order of that. In this way we can identify. See here, this is the output divided by input. See here, the output divided by again input, output divided by input, output divided by input. One by one you can simplify easily. This is only the expressions which I have shown you how we can simplify. See here how we can again check the stability of the system by looking this graph. Okay, so see here the poles and the zeros of the systems are plotted in the S plane. So the plane on which we are interested to show the poles as well as the zeros on the system is nothing but you are the S plane. to check the stability of the system. That's why this notation is the S for checking the stability. For checking the stability, this notation is the nothing but the S. Poles and the zeros. C H A omega. Conductivity. Here RHP is nothing but here the right hand plane and the left hand plane, and the entire is nothing but the S plane, that is nothing but for checking the stability of the system. This is the conductivity in the real and this is in the imaginary angular frequency. So in short, you can say we know very well S is in the frequency domain, small s is equals to conductivity plus J of omega, S plus J of omega, S plus J of omega. So see here, if all the period, what are the conditions here? RHP and the LHP, and if entirely is the S pole. So see conductivity and the imaginary part. So if all the poles of the system are lies in the left half means this portion. If all the poles of the lies in the left half, the system is said to be stable. If anything which is placed at this section means system is stable. Whereas if the poles is lies in the half plane is said to be an unstable. Right half plane. See here, if something is mentioned here that is nothing but the pole, so definitely it will be the what we can say, it is said to be unstable. If the things are here at the RHP, the unstable. If the things are here at the LHP, then the stability of the system. In this way, if the poles lies on the imaginary axis here, the system J omega is said to be imaginary stable. This part will be said to be imaginary stable. J of omega. So likewise, these are the examples how we can simplify. See here, G of S is equals to C by AS plus B. If A is equals to 1 and B is equals to 3 and the C is equals to 10, how we can simplify? What is mentioned here? The value is given, A is 1, the B is 3 and the C is equals to 10. So at that time, if you are going to place, so what is my, the value of here, the S, okay, see here, B is nothing but here, the B is equals to minus 3. Only the one pole of the system is lies at AS plus B is equals to 0, you can say. So what is A is nothing but the one is nothing, S plus B. S plus B. Okay, so what is my S plus B? S plus 3. Okay, if it is 1 here, so 1 into S, that is nothing but S plus, this is the 3. So again S plus 3 is equals to 0. So automatically S will be equals to minus 3. So that's why this minus term is coming in the left hand side, because this term is the conductivity is the plus value, here is the minus value. So it will come here. Okay, that is a minus 3 and here will be the what you can say, here is about because the left hand plane is here and the right hand plane. So in short, by identifying the S value exactly whether I am getting the S is positive or whether S is negative, depending upon that only we can place the poles and the zeros, because here we got S is equals to minus term minus 3, that's why left hand, okay, otherwise it will be on the right. Similarly, consider the following functions. Determine the whether the question will come like this. Determine whether the transfer function is proper or not. Calculate calculate the poles and the zero. Determine the order of the system. Draw the pole zero map and determine the stability of the system. So these are the four numerical is mentioned as a homework. How we can identify G of S is equals to S plus 3 and divided by S in bracket by S plus 2. Okay, so this is the form, this is in the order form, this is also order form, this is without order, these two are without order. So we can simplify in this way, we can identify. The other definition of the stability is nothing but the system is said to be stable if any bonded input uh, the output of the system. Okay, any bonded input, the output of the system is also bonded. So bonded input, bonded output, bonded input, bonded output, be both. Okay, thus for the any bonded input, the output either the remain constant or decreases, remain constant or decreases. See here the constant term before the applying the condition. So here will be the time domain which we have applied in the what we can say, this is again the unit step function. So here zeros and one. So by taking this one, you can identify this is a unit step input is there, and after applying the input as well as the output, so you will get as the after excitation you will get such type of a graph curve. So here you can identify this is the overshoot and this is the output and this was the input. Okay, so at that time we can identify easily. So see here the graph of a unit step function, how the things are coming. U of t is there, t is there, t 1, 0 and 1. Again y of t can be converted a raised to the power at. Why this is the plus 1? Because s plus of so and so is equals to 0. Okay, this is equals to 0. So that's why we can tell if for any bounded input the output is not bounded, the system is said to be unstable. If we are getting such cases, so at that time we can identify the instability. See example. G of s is nothing but output divided by input in the frequency domain. So here these terms are nothing but 1 by s plus 3. So automatically my s will be equals to minus 3. Okay, automatically equals to. See here the pole 0 map. If this is coming in this section, so unstable. If this is coming in this section, stable. Why we are saying these are stable and unstable? Just because by looking observing if cases here the s is equals to 3 plus, that's why in the right hand, whereas here the s is equals to minus 3, that is a left hand. So see here both condition, which is coming in the left is a what we can say stable function, whereas coming in the right is nothing but equal to unstable condition. So these are the few examples with order, without order. So this is the output. Output is equals to e raised to the power minus 3t of input. That is a u of t unit step function. So this is the with the help of the software and in the practical way you can identify easily whether you are going proper way in a proper way or not. So y of t is equals to e raised to the power again 3t into u of t. See here the twice they given the two examples that if they have shown the difference output is equals to e raised to the power minus 3ts, because in the previous s minus 3 is equals to 0, s plus 3 is equals to 0. So one time s was plus 3 and one time s was minus 3. So this if we are taking by considering this one with the help of the Laplace, so y of t is equals to e raised to the power minus st and e raised to power plus st. Okay, plus 3t as well as the plus 3t minus 3t plus 3t, and along with your input terminal, that is nothing but u of t, and this is the output. So how the if it's a minus sign if you are getting, then see the graph how that graph is decreasing, how this graph is increasing. Okay, plus is there, the graph is increasing. Likewise, that is a bounded input and the bounded output transfer function. Whenever one or more than the one poles are in the, that is nothing but the right hand planes, the solution of dynamic equation contains increasing exponential. That is a theoretical information here. So in short, today we have studied about, you can say, that is a transfer function, how the transfer function in the Laplace in the time domain to the frequency domain, that is denoted by Gs, and this Gs is nothing but the ratio of your the output divided by input, that is a V of t will be converted into the V of s, and what you can say x of, if you are taking the x of t, so that will be the x of s. So totally depend which parameter you are considering as a input. If you are taking u of t as a input, so definitely output y of t, then the y of t will become as a y of s divided by x of t will become as a x of s. Likewise, which you are taking the ratio, in short, output divided by input. And then later on we can identify the Laplace transformation with the help of the orders, with the help of the differentiation, with the help of the poles and the zeros, with the help of the stability, with the help of we can combine of the bounded condition, whether the bounded input and the bounded outputs are properly going or not. That is possible with the help of this what can say the network function, that is also known as your poles and the zero functions. So for the today we have taken the theoretical part related to the poles and the zeros. Okay, practically we will go to in the next lecture, and we will simplify the few numericals on the basis of your the poles and the zeros. Okay, so that is nothing but your the network function. On the basis of network function, we can simplify the few numericals. Thank you.